Okay, the first reaction that we have here is copper plus silver nitrate. You have it on your books, right? So we don't need to do that one. Aluminum and hydrochloric acid. It's a solid that is aqueous. That is what, well, we said they're all single displacement reactions. You will have to know, you don't know this by a fact, you're gonna have to be able to look at the activity series. The activity series is in your study guide. Let me show it to you just in case, because you need to become familiar with it. So the activity series is in your study guide, and we need to look at hydrogen and chlorine. Hydrogen is easy to find, because it's right here. No, I didn't mean chlorine, I meant to say aluminum. Where is aluminum? Right there, right? Aluminum is higher than hydrogen, therefore the aluminum will give its electrons to the hydrogen. So it's more reactive, and reactive when it comes to metal means I want to get rid of my electrons so I can have noble gas configuration, right? So if you see this happening, the one that is by itself is on top, then it's gonna happen. If it were the other way around, it wouldn't happen, right? If I had by itself copper and copper was trying to displace zinc, not gonna happen, you just put no reaction, right? So you need to know that. Now let's go back to this. Now the aluminum is going to end up as aluminum chloride, and then you're going to displace a hydrogen. What is wrong with that picture? Which is also a gas, right? Because hydrogen, if we see it is a gas in the table, it's green. And is there anything wrong with the aluminum chloride?
Should it be Cl2?
Cl what?
Cl2.
What is the oxidation number or the charge of aluminum?
It's +3.
Yeah, so it should be Cl.
3, but I thought it had to be 2 because it was diatomic.
No. The atomic is like hydrogen. These are good questions because it's when it's by itself. When it's combined, it's combined. But when it is by itself, you do have to say that it is something is diatomic. I don't know if. Okay. So now this is gonna be aqueous. You do not know it per the NaAA. That's not one of those. This is all chlorides, bromides, and iodides. All of them, when they're combined with something, they're soluble, but there are some exceptions, right? You don't know that, but I'll have to give you the solubility table for you to be able to know that it's aqueous. Now, if I'm going to draw the particle diagram for aluminum, how do I draw it? Brennan?
It's like a solid, so
Not molecules? Those are atoms for the metal. And I don't care what metal it is, this is how we always draw it. In reality, they all have different crystalline structures, but this is good enough for now because it's gonna tell us that we have a positive nucleus. You can just put the aluminum there, but it's a positive nucleus and it has a sea of electrons. No matter what metal, this is how we always draw it. Hydrochloric acid, I need to draw a beaker or some type of container to hold it because you know that we're gonna have a liquid. It's an acid that is aqueous. So aqueous means that it is separated. If you have hydrochloric acid, assuming it's something like this, assume this is your H and your Cl, it is not gonna be together, it's gonna be like that. So you won't call this a polar covalent bond, right now because that's not what's going to happen in here. This just means that they are aqueous, means they're separated. Do not ever put them together. I'm very generous on pop quizzes because it's a pop quiz and I'm trying to figure out where you are. But if I see those two together, you just get the point loss, no credit at all whatsoever. So it'll be the little H plus and the big Cl minus. If you want to know how many, I'll have to balance it. So how do we balance this, Ari? Because we have 3 chlorines, right? And now that, what do I do with the hydrogens? So, yeah, you can do that. You can put 6 hydrogens, or you can also know that you have 3 chlorines, so you're going to have to change that. So you have 6 of those, and then you'll do that, right? And then what? If you know how to do this one, you know how to do most of them. So that's balancing that equation. Now, I'm not going to draw 6, but that's what you will have to do. I'll never make you draw 6. It's way too many. So we're just going to draw 1 of each, or should we draw all 6? 1, 2, 3, 4, 5, 6. Obviously, they wouldn't be in order. They wouldn't be in order like that, so normally they'll be just going to be all over the place. But you do have 6, and for sure you know, which is the most important for me, I am not going to put an H and a Cl together. They're surrounded by water, right? They're surrounded by, they're in water shells, and it's just the ions floating around, because that's what that tells me. So if I don't see them together, this is wrong as well. There'll never be all the chlorines on one side and all the hydrogens on the other. I just decided to put them at the last minute, but they'll be all over the place, right? And there are a few ions in a whole bunch of water. This seems as a whole bunch of ions in little water. In reality, you have a swimming pool equivalent and just a few floating in it, in hydrated shells, right? Just a few. You don't have that superly concentrated to the point that you're almost having crystals. That's not what you have. Then we're going to have the aluminum chloride, which we also know is aqueous, but for the products, I'm gonna make a bigger beaker. And I put my water line because that's aqueous, right? And we're gonna have 2 aluminums, so I can do that. 2 Al 3 pluses. Little. And then you have how many chlorides? You have 6 of them. So 1, 2, 3, 4, 5, 6. That's what you have in your products. And then you have 3 hydrogens that escaped as a gas. So you're going to have the 3 hydrogens. 1, 2, and 3, and all of those escaped. I did not draw what happens in the middle. I'm going to do it now. But this is basically the representation of that equation. What do we have at the beginning? What do we have at the end? That is literally what's happening there. You know that the chlorides were negative chlorides here and negative chlorides there. They didn't do anything, so those are your spectator ions. They were aqueous ions in solution, and they are aqueous ions in solution again. Those are your spectator ions, because they didn't do anything. The aluminum went from a solid to an aqueous ion, so that changed. and the hydrogen went from an ion in solution to hydrogen gas. So that changed as well. So if I'm going to write the complete ionic equation, I'm going to write this. I'm going to have 2 aluminums that are solid plus 6 hydrogens, ions. I'm writing this, 6 hydrogen ions, and then 6 chloride ions, 6 chloride ions. That's what I have here. I'm writing what I truly have. I have 6 hydrogen ions, 6 chloride ions. They're aqueous. That's solid. And that goes into, I have 2 aluminum ions, aqueous, 2 of those. And then I have 2 of these ones. So 2 of 3s is how many? 6 chloride ions, they are aqueous, plus 3 hydrogens, and they are a gas. Either by doing the sketch, which you will not always do, or by looking at the equation, which you may do more often, you are going to see that the aluminum went from solid to aqueous, the hydrogen went into a gas, the chloride was 6 chlorides and 6 chloride aqueous. It didn't do squat. So those are your spectator ions. And all you really had in this single displacement reaction is aluminum that was unstable because it was a solid, so it was unstable, ran into the hydrogen ions. And for every aluminum, you gave to 3 hydrogen ions your electrons. Then when the hydrogen got the electrons, it escaped as a gas, and the aluminum jumped into the solution. So let me do the middle step. But if the middle step confuses you, then I just wanted to show you the whole reaction, which is perfectly fine to write on a quiz, the whole reaction. You don't have to write the middle step. Middle step is understanding what happened. I had my aluminum chloride, I had my hydrochloric acid, and I went ahead and put a bar or a strip of aluminum in there, or I put this. I put a can of aluminum, right? I put a can of aluminum and I dip it into the batch beaker with hydrochloric acid, which is what we are gonna do. Maybe I need to do that next time when you all present. I just need to go ahead and do it. So you see this reaction, and as soon as you put it in, you're gonna see a whole bunch of bubbles. It's gonna get really hot, and you're gonna see the hydrogen blowing out, going out. So I'm gonna put a strip of aluminum or a can of aluminum. I'm just gonna put aluminum in there. I'm gonna dip it in there. As the hydrogens are going by, and if I use a very low concentration, it takes forever for this to happen. It won't happen this quick. If I use like a 1 molar hydrochloric acid, you won't see a thing. You may see some little bubbles forming the side of the can, but you won't see anything excited. I've got to get to about 6 molar for you to be able to start seeing things. Why? Because 6 molar is more concentrated. So every time you have 3 hydrogen ions going by there, you have another 3 hydrogen ions going by here. The chlorides, we don't care, but I can draw them. The chlorides were everywhere. 1, 2, 3, 4, 5, and 6. We don't care about the chlorides really. What's happening is when the aluminum is in contact with those hydrogens, there is a voltage. It's kind of love between them, right? There is an attraction. And through this attraction, the aluminum, which is more reactive, is going to be, you know what? The hydrogen is too happy. I'm going to get in there, give it my electrons, the 3 electrons that it has to get rid of. And that's why the equation tells you that for every 2 aluminums, you make 3 molecules. Because every aluminum gives 3 electrons to the hydrogens, and then you make 1 molecule, 2 molecules, and 3 molecules. When we did the silver, remember the silver became a solid, right? And it just was plating right there. And we could drop it and it could fall to the bottom because solids are denser than the water, right? So it'll fall to the bottom. Hydrogen is not a solid. And hydrogen cannot be by itself. You cannot have one little hydrogen by itself, as some people were putting in the sketches. They were putting one hydrogen coming out. You can't have hydrogen by itself. As soon as a hydrogen has another hydrogen, it immediately combines and it becomes a diatomic molecule. At that point, it becomes a gas and it comes out of the solution. So these two hydrogens will join together and it will come out as one hydrogen molecule, and then two, and then three. This is what's happening. So I had Reese first, I think. What was your question?
I'm confused because I thought that hydrogen was the same before that happened.
You have hydrogen ions. When I have hydrochloric acid, which I should have some over here, when I have sulfuric acid, similar. What I have in here, it could be hydrochloric. I could just tell you this is hydrochloric. It's not. But when I'm looking at this, in this bottle, I have, assume it's hydrochloric. It will look exactly the same. I have hydrogen ions, and I have chloride ions. Hydrogen is more stable everything is more stable as an ion, right? So those ions are quite happy to be there. They're all quite happy to be there, right? They're all stable ions. It's like when I put salt in water, I no longer have salt, I just have ions of sodium and chlorine, electrolytes, right? You have electrolytes, it's separated. But they're happy, they're not gonna come out, they're not gonna join anybody, they're not gonna do anything because that's the most stable way for hydrogen to be. It's combined, making a salt, or it is an ion in solution. Either way, as long as it's an ion, it's very stable, very, very stable. So the hydrochloric acid will look like that, Reese. And when it is here, as soon as any of them gains the electron, because that's what's going to happen, the aluminum is going to push it. As soon as it gains the electron, it'll immediately join another hydrogen, and it will come out as a hydrogen gas. So as soon as these hydrogen atoms are formed, as soon as it stops being an ion, it becomes a hydrogen atom. As soon as they do that, they join another one immediately, and then they come out as a gas. Does that make sense? And these are the things I wanted to clarify because I definitely understand. It's not like, oh, how could this person do that? No, I know. I know what's happening. We always had ions, and the ions sometimes fell down, and so it was important for us to go over this together. So the people that did the assignment will get the bonus, right? I just realized I need to go ahead and correct it, and hopefully you all correct it in your sheets of paper so that you have this right. Because obviously people were not trying to do a bonus and get it wrong. And it was I don't know, if there were two, the first two I tried to grade, they both had issues, so I just stopped. It may be that the rest of the class was fine, I don't know. Now, the next reaction that we have here is, yes, sorry, I forgot, and I erased it too, but we can get it back. Okay.
Can non-metal like displace non-metals?
Yes, that's what we're gonna do that. That's the last thing we're gonna do. So we have the second one that we have, or you want me to do the non-metal? Doesn't matter. Okay, so the second one reaction that we had for today was sodium plus water. Alkali metals, all alkali metals, when you put them in water, all of them, and it's just alkali metals. As soon as you put them in water, I like to draw it like this because I know it's gonna be a single displacement reaction. If you were to look at the table, the sodium is higher than the hydrogen, so is the lithium, so is the potassium, so is the rubidium, and so is the cesium. They are all higher than hydrogen. very fast, very reactive, very exothermic. I don't care what the concentration is. I mean, not concentration, you have a metal, so that's 100%. So you have the sodium is going to displace my hydrogen, and I'm going to end up with NaOH plus the hydrogen that gets displaced is going to be on the side. But what do I do to that hydrogen, Hannah?
Add to
Gas, right? Because it could never be by itself. And is this aqueous, Sophia, or is it a solid? Sodium hydroxide. Think of NaA, right? It's NaA, and that is what? Alkali metal. That's one of your A's, so that's going to be aqueous. Most hydroxides are not, but this one is because it has NaA. So that's aqueous, that's a solid, that's a liquid, that's not aqueous. Water is a liquid. So how do we draw this? We put the sodium, I'm not going to keep asking this, but I hope you know that the sodium metal will be, I don't care what metal we do, it's just going to be protons surrounded by a sea of electrons. And then I'm going to add water. So water obviously has to be in a container because it's a liquid. Let's balance it so I know what I'm doing and how many I need to draw. We have one sodium, Fairfax. Well, the sodium will be the last thing actually that I balance, and the hydrogen. I should think about the oxygen, but the oxygen is balanced, so then I think about the hydrogen. What will be the hydrogen? I have 2 over there, and I have 3 over here. So in order, that's an even number and that's an odd number. So it'll be good to make this an even number as well, right? So in order to do that, I'll put a 2 here. That means that I have how many hydrogens? 4. And how do I get 4 hydrogens there? No, you multiply it times 2. Because that will be, it's H2O, which I wrote it wrong for balancing, but if you had seen the H2, it'll be more clear to you, right? H2O, and then what do I need to do to the sodium?
you need to add a 2.
Yes. Right? Now we're balanced. And yeah, that's written odd. It's good for the single displacement, but when you're doing the sketch, you need to know that water is going to have 2 water molecules. That's just the ratio in which they react. It's not that you only have 2 water molecules. That's the ratio in which they react. And we're going to talk a little bit more about that. And then in the bucket, once I put the metal in here, I'm going to go ahead and draw my products because that's all you really need to know, although I will talk about the intermediate step. So in the products you have, how many sodiums maximum? You have 2 sodiums in here somewhere. And these are ions in solution, so they have a +1. And then you have 2 hydroxides. And they're separated. And you also have hydrogen gas. Oh, just 1. 1 hydrogen gas that is exited. That is your complete particle diagram. And I'm doing this because I know that you're struggling, so putting the intermediate step may actually be confusing things. That's just understanding more than having to draw that. This is a representation of what you see on top. 2 sodiums, 2 hydroxides, 1 hydrogen gas. That's all you need to draw if I ask you for products. You do not have to draw the intermediate step, right? I have a feeling that's what's been confusing people. However, I do want to know what happens, but let's go ahead and do the complete, yes.
Why did we draw the water in like Is it like in a solution? Or is it just...
It's just water, it's liquid water. Obviously you won't have 2 molecules or 2 moles, you're gonna have way more than that. But that's the ratio in which for every 2 sodiums you use 2 waters and you make 2 of that and you make 1 of those. But that's just water, that's a cup of water, that's this, right? But the ratio is for 2 sodiums, I'll use 2 waters and I'll make 2 of those and 1 of those. That's the ratio. So let's talk about the complete ionic equation. It'll be 2 sodiums. How many hydrogen ions, Ari? 4? Say 4 and I write 2. 4 H pluses. You could have written this as 2H2O, right? And actually when I do 2H2O, people tend to put 2H2s. Water is a Mickey Mouse. It's got the 2 hydrogens and the head, right? I don't know where my red is, but it's got it. But it has 2 of these. So, no. You have 2 waters. Water is a liquid. You leave it together. 2H2Os. You do not separate it. It doesn't say aqueous. I'm glad I did that. It does not say aqueous. It says liquid water. Liquids and solids and gases are left as molecules or are left as the lattice. They are left as what they are. The only thing that we separate is something that says aqueous. So sorry, I've been separating way too much. Now that one says aqueous, so that I have to separate. So you have 2 Na positives. How many OHs, Elizabeth? Plus 2 OH minuses. You see how I'm adding the charges? Because in reality, you have the charges and you have 1 H2 gas. That is your complete ionic equation. You have your sodium. We don't draw just 2 atoms, but this one we draw 2 waters, and it has 2 sodiums, 2 OHs, and then you have the H2 gas that escaped. It's literally a representation of what you have. The sodium solid became sodium aqueous, stays. The water became OH and H, stays. The complete and the net are the same. Not everything changes, right? Everything got disturbed, everything reacted. That is the same net ionic equation. You do not have there's nothing I can cancel, everything changed. So I cannot do that. Now, what happened in the middle? If we were to just draw the intermediate step, if I say, hey people, draw the intermediate step, then you have to say, hey, I had sodium, I put it in my water, which is what we are going to do as soon as this silly thing arrives, whenever it arrives. I have my sodium atoms, these are atoms, with their sea of electrons that they want to get rid of, just 1 per atom, right? And then this is the weird part, it's so reactive that what comes in contact with this is an H2O. Right? It's water, it's literally water. It's not an ion, it's not a hydrogen, it's literally water. And sodium is so reactive that it doesn't care that water is happy and content to be what it is. It doesn't care, it's so reactive because that's the most reactive metal. Each sodium will give an electron to the hydrogen, and that is gonna leave behind an OH minus. So this OH minus stays by itself. I really shouldn't make it red because OH is a base, so I may need to leave it at that. But that's my OH minus. So we end up with these little things that are OH minuses. You end up with 2 of those. And the hydrogens go from just being happy there to all of a sudden being a complete atom. And two of those atoms join and make your one hydrogen that goes out. For every two sodiums, you put two electrons in the hydrogens in two water molecules, and you end up with one hydrogen atom, or one mole, not atom, molecule, one mole of hydrogens, or one molecule of hydrogen that goes out. This is the hard part, understanding what truly happened. Now, questions on this? Let's do the last one, and then we'll do another reaction, and then we'll talk about the project. The last one is should have it memorized by now. We have 2Na sodium bromide, chlorine. Okay, in this one, when you see it, you're gonna try to replace the wrong thing. I'm just telling you, you're gonna try. You need to look at it and see what Autumn was saying. Chlorine, electronegative, they want to steal, right? Something like chlorine, actually in the same family, so they're all the same. They're all the Fairfaxes, right? And the family of Fairfaxes. They're all going to want, well, that's not nice. But they're all the non-metals, right? So they're not going to be replaced by somebody who wants to give. They're gonna replace, the chlorine is gonna replace the weaker bromine. Because fluorine is the most reactive, chlorine is a little bit less, bromine a little bit less, and iodine is the least reactive of the halogens. They are all crazy reactive. All of them. We were talking before about metals they want to give. Now we're talking about the non-metals they want to take, right? These are all in the same family, and they literally, one will displace the other. So you are going to have sodium bromide was aqueous, and then you have chlorine as a gas. I have to tell you this state of the first one, because you will know if it's in water, it'll be a salt, but you need to know that because you also have that salt, right? You could have sodium bromide as a salt. So I need to tell you that. You're gonna have a container that has, well, we already know, the sodium bromide, the chlorine replaces the bromide, so you end up with an NaCl, literally salt. And you know salt is aqueous. It's got the sodium. That one has the sodium as well. And you're going to end up with a Br2. Some of it will be liquid, some of it will be gas, but when I've done this reaction, you really see the gas coming out. Although you see that bromide is normally a liquid, you do see the gas come out. So we're going to say, hey, a gas is going to be displaced in a gas.
Bromine one with diatomic.
All of the, yes, it's hydrogen, then you go to nitrogen. It makes a 7, and there are 7. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. It covers them all. So yes, it is gonna displace it. You have two sodiums, two chlorines, two chlorines, two Brs, that's balanced. So we're gonna have two sodiums and two Brs. All totally happy, all totally stable. But then you're gonna bubble, you're gonna put a hose or something, and you're gonna bubble chlorine molecules through it, right? You're just gonna bubble that through. This bromine is totally happy because it has stolen an electron when the chlorine wants it. You may think that chlorine, because it's diatomic, is more stable. No, ions are always more stable. yes, you can never have bromine by itself, and when there are two, it's more stable. But there is nothing better than to get rid of that and having noble gas configuration. That's the most stable thing. So when the chlorine runs into the bromine, well, I put them both together. So in the reactants, I really should have put the chlorine over here as a gas, right? In a closed container. That would be your chlorine, your Cl2. But then you're gonna have your container, and you're gonna have to bubble the Cl2 through the chlorine bromide, and you're gonna end up with 2 NAs classes. I'm just drawing that. You're gonna end up with 2 Cl minuses, and you're gonna end up with 1 molecule of bromine. Br2. Some of it may stay as liquid, some of it will come out as gas. So now what is happening, I'm not going to draw the intermediate step, but what is happening is when the chlorine is bubbled through this, just imagine the chlorine goes close to the bromide, and it goes, I'm taking that electron, and I'm going to make you turn into a gas, and it takes the electron. Chlorine is more reactive. In this case, it's going to take an electron, not give it. It's going to take an electron. Now the chlorine is going to be happy in the solution. That makes it happy. And the bromine has to leave. The bromine has to leave. Does that make sense? Now, let's take a 2-minute break. And then we're going to do another reaction that is not single displacement, it's a combustion reaction. And then we move on.